Alright, so now mathematically, when you're trying to determine a limiting reagent, let's do a sample problem, and I'll show you how to do that. So let's say we have 125 grams of CaCO3 reacting with 125 grams of HCl. And you need to know the chemical reaction, because you need to know the balanced coefficients for these. So I'll give you that. And just for the sake of time right now, I'm not putting in phases, but phases are important, but again, it's just for make it go a little quicker. Okay, so this is our balanced reaction, right? So we see that calcium carbonate and hydrochloric acid react in a 1:2 ratio. So, to figure out, so can you just look at that and say, well, HCl reacts twice as fast, and we have the same amount, so HCl is going to get used up first. The answer is no, because be careful when you're looking at this. You don't really have the same amount, you have the same mass, right? But that doesn't mean necessarily that you have the same amount of moles. So we have to get this into moles before we can compare. So the best way to do this, determine the limiting reagent, is to take both of, or not, however many reactants you have, take all of the reactants you have, and figure out, theoretically speaking, how much of any of the products they would form if it was entirely used up. And it doesn't matter which product you choose, just choose the same product for each one. And you'll see why, because it makes the next part, it makes the percent yield calculations pretty simple if you do that. So, let's do that first with calcium carbonate. So we have 125 grams of calcium carbonate. So the first step, as I've said before, you need to, whenever you're comparing two different compounds in a chemical reaction, you need to get into moles. So we need to use the molar mass of calcium carbonate. We need to cancel out this unit of grams in the numerator, so grams goes down here, moles up here, and it's 100 grams per mole. So now we're in moles of calcium carbonate as our unit. Now we need to do a mole to mole ratio between that and one of our products. It doesn't matter, but let's choose CO2. So this is moles of calcium carbonate, so we need to put that in the denominator, so it gets canceled out, meaning moles of CO2 goes up top, and it happens to be a 1-to-1 ratio, so just 1-to-1 here. That's not always going to be the case. So now we're at moles of carbon dioxide, and then the last step, we want to figure out, I suppose you could stop at moles, but especially if you're doing percent yield calculations, it's a lot easier to look at the numbers of mass, and in percent yield, you're definitely going to want mass. So let's take this next step, since we know how to do it now, and go from moles of CO2 back to the mass of CO2. So now we have to cancel out the units of moles here, so now moles goes on the bottom, and grams on top, and the molar mass of CO2 is 44 grams per mole. And if we multiply all the numerators across, multiply all the denominators across, and divide, we get 55.0 grams of CO2. So what that's saying is that, hypothetically, if every last bit of calcium carbonate is able to react, we would get 55 grams of carbon dioxide. And remember, I said the limiting reagent is the one that reacts entirely. So that's implying that if this is your limiting reagent, you'll end up with that much CO2. Now let's do that same calculation for hydrochloric acid. So we have 125 grams of HCl. Put that over 1. Now we have to use the molar mass. So we just do the exact same setup. We basically just plug in the information for HCl instead. So the molar mass for HCl is 36.45 grams per mole. Then you cancel it out. Now we do the mole to mole ratio between HCl and carbon dioxide. Again, now I do have to choose carbon dioxide because I chose it the first time. So again, it doesn't matter which product you choose, just as long as you use the same product for each calculation. So now this is not 1-to-2, right? This is actually 2-to-1, right? So we put 1 mole of CO2 on top and 2 moles of HCl on bottom. Now we can once again use the molar mass of CO2 to get back into mass, and that gives us an answer of 75.4 grams. So that means hypothetically speaking, if every last bit of hydrochloric acid is able to get used up, we could produce 75.4 grams. So which of these is your limiting reagent? It's always going to be the one that gives you the smallest mass. And the reason why is because remember, these are reacting with one another, right? So they're producing the product at the same rate because it's the same reaction, right? They're reacting with each other. So at the point that we hit 55 grams, we just said that means that calcium carbonate has run out at that point. We've used it all up. But look, hydrochloric acid, we could still produce more. That means inherently that there has to be more hydrochloric acid there. So this means that calcium carbonate, since it can't produce as much, that means that would run out first in this reaction. Thus, calcium carbonate is your limiting reagent. So if you're just asking to, if you're just being asked for the limiting reagent, that's your answer right there, calcium carbonate. Now, let's say you're asked for a percent yield. Percent yield, so what that is talking about, chemical reactions rarely work perfectly. So again, we can do this calculation and say, oh, it should produce 55 grams of carbon dioxide. But a lot of things have to happen properly when mixing chemicals in order for reactions to take place. So reactions almost never happen perfectly. So we can say that that's how much should be produced, but it's very rare that we actually get that number. So one way to quantify the success of a chemical reaction is by percent yield, saying how much mass did we get in our final product compared to how much we were hoping if everything worked perfectly. So percent yield is calculated as follows. It's the actual yield over the theoretical yield and then you multiply that by 100 to get it into percent. So the theoretical yield, that is what we just calculated. The theoretical yield is the mass we get from our limiting reagent. And that's why doing figuring out the limiting reagent this way is nice, because it saves you a calculation that you'd have to do down the road anyway. So it's a theoretical yield because, again, that's saying if every little bit of this reagent reacted perfectly with the other reagent, everything went exactly as we could have hoped, and we got every last bit of product possible, that's how much we would produce. Right? So that's your theoretical yield. An actual yield, that has to be determined experimentally. So it would be something that you would determine in lab, or in a word problem, you might say like, oh, this student, runs this experiment and actually gets, this much. So let's say, they actually get 50 grams. Right? So 50 grams would be our actual yield. This 55 that we calculated would be our percent yield, or I'm sorry, would be our theoretical yield. Multiply that by 100, and that gets us 90.9%, and that would be our percent yield.